So when talking about sums of series, particularly to alternating series, there's lots of alternating series that we know the sum of. And although it's a bit redundant, I'm going to point it out anyway. If we know the sum, they have to be convergent because we know what this series add up to when we add infinitely many terms. So for instance, the alternating series of negative 1 to the n over n factorial. So we're looking at from 0 to infinity. So we're looking at starting at 1 and then going to minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial, so on and so forth. So we start at 1 minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial minus dot, 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 dot. When we add all that up, we know we get 1 over Euler's number. Okay? And so it comes up to a finite value. We physically know what that value is. And so there's lots of these series that we know the values of. And I think it's kind of interesting, and I don't have an answer for this, but I think it's kind of interesting that when we're talking about finding the sum of these series, a lot of times it has either something to do with Euler's number, something to do with a trig function, or something to do with a natural log. I think it's kind of an interesting phenomenon. We'll learn more about that in the next unit as to why that is the case. But I just think it's kind of an interesting observation. When we talk about p-series specifically, so these are the p-series families. And these are not alternators. These are just your traditional p-series. Here are the sums for p-series that are even powers of p. So n squared, n to the 4th, n to the 6th, n to the 8th, n to the 10th, etc. And if you notice, these have pi in them as part of their sum. Again, kind of an interesting phenomenon related to trig functions. Odd numbers, and again, this is your traditional p-series, so this does not alternate. So this does not alternate. So the odd powers of a p-series, we don't know. We don't know the value of those sums for some reason. Not quite sure why. So just kind of some interesting phenomenon there. So when we talk about this idea of convergence, particular to alternating series, so this is definitely focusing on alternating series here. We have this situation of either being absolute or conditionally convergent. And so if we take a look at that phenomenon, what this is saying is if this is an alternating series, and we remove the alternator, then we can call, and this converges, we call it absolutely convergent. If this is an alternating series and we remove the alternator, and we find that when we remove the alternator, and I put that in the wrong spot. This is when we remove the alternator. And the alternating series converges. So the alternating series converges. But when we remove the alternator, what's left diverges. We call that conditionally convergent. Okay? So if we take a look at that, then let's take a look at this series. It's not a p-series because it alternates, so it's not one of these because it has an alternator, and it's one of the series we know as sum 2, and it's right here. This is the one we're looking at in the example. Okay, so it's and it's a really popular one, right? This 1 over n pattern is really popular. So let's take a look at this. So we're going to take a look at the series of the absolute value, in other words, without the alternator, the absolute value of a sub n. So for this particular problem, we're looking at 1 over n. And so if we look at this particularly, then this is a p-series. P is equal to 1, so we know it's divergent because it meets the criteria for divergent p-series. So without the alternator, we have divergence. So we can't have absolute convergence because we already have a divergent situation here. Now let's take a look at this. It's an alternating series, so we're going to use the alternating series test. We're going to take the limit of 1 over n as n approaches infinity, and that's 0. So the first criteria has been met. Then we're going to take a look at a sub n, and we're going to compare it to a sub n plus 1 and make sure that that next term is smaller. So we're going to take a look at 1 over n, and we're going to compare it to 1 over n plus 1 and go through that mathematical derivation. So we've got 1 times n is less than or equal to n plus 1, which is a true statement. And so we know that this, in other words, for this problem in particular, we know that with the alternator, as n goes from 1 to infinity, diverges, excuse me, I said that wrong, converges because of the alternating series test. So we have the alternator converging and we have the non-alternator diverging. So we call this conditionally convergent. So looking back at this example from the previous section, we have this p-series, 1 over n squared. And if we go back to when p equals 2 here in this chart, oops, excuse me, I checked off the wrong one. When this power is equal to 2, which means p is equal to 1 here as it's written, we have a sum of pi squared over 6. So we know the sum of the series is pi squared over 6. And so this is the one where we found the expression for the sixth partial sum when it alternates. So this is this phenomenon again of looking at the absolute value of a sub n. That's what this series represents. So at n equals 0 to infinity of n squared, that's that absolute value phenomenon. And we know it converges because here's the sum. I mean, we don't have to do a test on it. We could do a p-series and come to that same conclusion, but I mean, really, we've got the sum expressed right here. So we know that converges. And now let's take a look at our alternator. So if we look at the alternating series, see if I can get both of them displayed at the same time so we can see both expressions. There we go. So we've got 1 plus 1 over 4 plus 1 over 9 plus dot, dot, dot. When we look at the alternating series, so as we express it consistent with the last page here, the sum of a sub n, so we have this alternator here over n squared. So the only difference between this and this are the alternators. Then we have, instead of this sum, we have 1 minus 1 over 4 plus 1 over 9 minus 1 over 16, and so on and so forth. So if this sum is pi squared over 6, then with this series having this alternating plus minus, having this alternating sign here, plus minus, then what about the sum of this in comparison to this? And so if I give you a second to think about that, you're going to come to that conclusion that this sum, the sum of this series, is going to be less than pi squared over 6. So because we're subtracting off values, and we're not just adding values like we were up here. So since we're subtracting off some of the value, we're going to come to a series here that is less than pi squared over 6. So if we can show that the absolute value is convergent, if we can prove that through a p-series test or whatever, then if we stick an alternator with that same a sub n term, this has to converge. And we can conclude that now even without doing the alternating series test, because this has to have a value, a sum, that is less than this sum. And we know this sum. So that's what leads to this theorem here. We say if we have this expression with no alternator and it's convergent, then the expression with the alternator, so this is no alternator, and that converges, then the expression with the alternator, must also converge, because it's got to go to a smaller sum. So what we're going to do with these examples is we're going to try to use Theorem 816 on that previous page to make these proofs a little more compact, a little quicker. So if we look at this, I just want to rewrite this so that you recognize it as a p-series. Minus 1 to the n plus 1 over, this is n to the first power, this is n to the half power, so this is n to the 1.5 powers, which would be 3 over 2. Okay, so let's take a look at, let's use Theorem 816 and take a look at the absolute value type series. So that means we're taking a look at an absolute value series, similar series, so that basically means just wipe out the alternator, don't include the alternator. So we take a look at this, we say it's a p-series, we have a p of 3/2, which is greater than 1, so we know that this converges because of the p-series test. So we know that the absolute value converges, so therefore by Theorem 816, and you don't even have to write that. But I'm going to reference it since we just looked at it. By Theorem 816, then this, the alternating series of the same form, also converges, and therefore is absolutely convergent. Because both the series itself converges and the absolute value expression converges. If we look at the next one, 1 over n, let's go ahead and look at the absolute value series. So we're looking at n equals 1 to infinity of just 1 over n. And we're also, you notice how we're really relying on p-series and geometric series. That's a reoccurring theme. Those are by far your most popular tests. So we look at a p-series test, p equals 1. So we know that this is divergent because of the p-series test. Okay, so we know that absolute convergence is out. So all we can go for right now is conditional convergence. Okay, so we do have to do another test. Now it is all up to the alternating series test to see if we can get any convergence whatsoever. So we're going to go ahead and set up our alternating series criteria. We're going to take the limit as n goes to infinity of 1 over n. And that, and put an infinity there, we get 0. So we get the first criteria met. We've done this a few times already. We're going to check to make sure that it is non-increasing. So 1 over n plus 1 is less than or equal to 1 over n. And simple cross multiply n less than or equal to n plus 1, which is true. So this series is conditionally convergent. Okay, because this alternating series, I just forgot to finish the power expression there. This alternating series did converge, but the absolute value series did not converge. Okay, if we take a look at this series, we're getting a little more complicated, but let's again kind of stick with this theorem 816 and go after the absolute value of the series. So we're looking at 2n plus 3 over n plus 10 as n goes from 1 to infinity. And so anytime you start to have expressions like this, you should be looking at finding the limit, doing the nth term test. So we're going to take the limit as n goes to infinity of 2n plus 3 over n plus 10. I'm going to do a L'Hopital's. That should be real quick. So taking the limit as n goes to infinity, take the derivative of the top, which is 2, the derivative of the bottom, which is 1, and so the limit is 2. And so we know that then the 2n plus 3 over n plus 10 diverges because of nth term test. So we know the absolute value form of this series diverges. So kind of like the last example, we can't go after absolute convergence. The best we could possibly do is conditional convergence. So let's go ahead and look at the series now with the alternator. And so basically we're just doing this test if we have to, you know, if we don't get convergence up here. So let's take a look at this. So kind of, if you notice, we're starting off the same way, right? We see the alternator. We're going to go and do our two conditions, but this first condition is really doing this. I mean, that's our first condition, right? We have to take the limit of the a sub n, the 2n plus 3 over n plus 10. And I didn't write the 0 for the 10 here. It doesn't change any of that, though. As n goes to infinity, and we get 2. And so at this point, the alternating series test doesn't work. It turns into the nth term test. So we know that this is not applicable. We don't even need to do that because the first criteria hasn't been met anyway. So not only does this diverge without the alternator, but even if we keep the alternator in, it still diverges. So we just call it divergent then. There's some people like to call it absolutely divergent. That kind of that term doesn't really exist. This is just divergent in either case.